It's also great to see that Quate is here. He's an American engineer and physicist. He graduated in electrical engineering at the University of Utah and then moved to Stanford, where he obtained his PhD in 1950. In the decade after 1950, he worked at Bell Labs in Murray Hill, New Jersey, and then at Sandia in Albuquerque, New Mexico. He moved to Stanford University, where he's been a professor of applied physics and electrical engineering since 1961. Quate has been interested in scanning probes for a long time. Together with Russ Lemons in the early 1970s, he developed a scanning acoustic microscope. This instrument has been used to study the structural properties of devices, as well as the elasticity of tissues. In the mid-1980s, he became interested in realizing an instrument that could provide images of surfaces with very high resolution. Together with Gerd Binnig and Christoph Gerber, he developed atomic force microscope. And I've been honored to deliver his notes, so please hear what he has to say. This adventure began on a flight from San Francisco to London in 1982. For months, I had been pondering the future of our microscopy research group at Stanford. We had just completed our work in acoustic microscopy and were looking for a new direction. I considered a variety of products, such as the building of an X-ray microscope, but nothing fell into place. I thought that the trip to a conference in London might provide some time to get away and think. On the way to the airport, I picked up a technical magazine called Physics Today to read on the plane. Once on board, I found an article about Gerd Binnig and his new technique of scanning a sharp tip over a metallic surface and measuring the distance between the tip and the sample. It was called the Scanning Tunneling Microscope, STM. This was something I had to see for myself. In London, I changed my travel plans and went to the IBM lab in Zurich. It proved to be the start of a journey into a whole new world. What I saw in Zurich was amazing. The STM combined simplicity and amazing spatial resolution. Binnig hadn't seen individual atoms yet, but he was close. I was so inspired by the new technology that when I returned to Stanford, I selected a group of students to work on a new project to explore the capabilities of the STM. One student made a low-temperature STM. Another student made an STM in ultra-high vacuum. Others made an STM that worked in air. The STM was a big scientific achievement. In fact, the inventors, Gerd Binnig and Heinrich Roeder, went on to earn a Nobel Prize in Physics in 1986 for their work on the STM. However, the STM had a major limitation. Since it depended on the flow of electron tunneling between a sample surface and the tunneling tip, it could only image conducting materials. Furthermore, most conducting materials, such as metals and semiconductors, are easily oxidized in ambient conditions, which require the STM to be put in a vacuum chamber. I invited Gerd Binnig and Christoph Gerber to come to Stanford for a year. When they joined us in 1985, we wanted to see if we could create a microscope based on the principles of the STM, but that could image any surface, regardless of electrical conductivity. The solution we discovered was to add a second tip. We made a tiny flexible cantilever out of metal foil. We glued a sharp diamond tip onto the cantilever, working by hand under a microscope. We inserted this cantilever assembly between the sample surface and the STM's tunneling tip. This allowed the device to work on all surfaces, not only metals. As the cantilever's diamond tip scanned across the surface of the sample, the interatomic force between the sample surface and the cantilever's tip caused the cantilever to bend. The STM tunneling tip then measured the bending motion of the metal surface of the cantilever. In this way, the AFM was born. A for atomic resolution, F for force on the cantilever, and M for microscope. We published our 1985 work in Physical Review Letters in March 1986. The early AFM images were far from atomic resolution. Some people doubted that atomic resolution was possible, but to me, the potential was exciting. I knew that we would need patience, trial and error, and a diverse group of brilliant people. We built a group of bright, creative folks from different disciplines. chemistry, computer science, mechanical engineering, physics, and electrical engineering. I would pose challenges to them. For example, how can we see rust happen at the atomic scale in real time? A crazy question like that would provoke our multidisciplinary team to come up with dozens of crazy ideas. Ideas that it would test 24/7. It was an environment of motivation, hard work, and fun. In order to pursue these ideas, the team had to invent things. Sometimes they worked, and sometimes they didn't. While we're never able to see rust happen at the atomic scale in real time, that was not the point. The point was that a diverse group of students, when given a framework and a single problem to guide their thinking, created a cornucopia of inventions. We knew that better cantilevers could be made by microfabrication techniques, similar to how integrated circuits were made at the time. Our goal was to build microfabricated cantilevers with sharp tips built in as part of the fabrication process. However, to get started, we fabricated cantilevers that were simply flat diving boards without any special sharp tip. Even so, Gerd Binning thought we could use the corner of the diving board as a crude tip. Binning, who was by then back in Zurich, successfully used these cantilevers to scan graphite, showing the atomic corrugations at the expected spacing of the atoms, similar to what was seen on graphite with the STM. At Stanford, we used the same kind of cantilevers to image boron nitride, an insulator with a structure similar to graphite, showing the same kinds of atomic corrugations. This showed that the AFM could achieve STM-like resolution on all surfaces and was not restricted to electrically conducting surfaces. Seeing periodic corrugations at the right spacing wasn't quite the same as truly seeing individual atoms, but it gave us the first hint that atomic resolution might be possible. We later learned to make microfabricated cantilevers with sharp tips built in as part of the fabrication process, as we had originally envisioned. These kind of cantilevers are still used today. With the new cantilevers, we were able to examine virtually any molecular surface. Nearly every sample we put into the AFM revealed something new. The team made AFMs that operated in aqueous solutions, in acidic environments, at liquid nitrogen temperatures, in a vacuum, in liquid helium. We used the AFM to look at the new superconductors that all the rage at the time. We looked at silicon, germanium, gold, and diamond. If it was on the periodic chart, chances are we looked at it. We used AFMs to scratch a line at near atomic scale. We imaged biological samples. We looked at living cells in action, the molecular structure of DNA, and we tried to move it around. We were able to use the device to examine surfaces for any imperfections. For example, we could inspect silicon wafers or silicon chips to find irregularities before they went into production. The device enabled the development of reliable, error-free nanoscale components. It eventually became evident that the two-tip design of the AFM had a weakness, the STM tip. The tip that was on the back of the AFM's cantilever exerted its own unwanted force on the cantilever, making it a noisy sensor for detecting cantilever motion. Other systems have now replaced the STM tip in AFMs, such as the optical interferometer and the optical leveler. The AFM has evolved in other ways as well. The AFM research community has developed better tips, better cantilevers, better detection systems, better scanning systems, and better control systems, all of which has made the AFM a useful and practical instrument. The fact that the AFM can operate in air, in a vacuum, or in liquid is a huge advantage over other microscopy techniques. Vast number of AFM modes have been introduced to image, measure, manipulate, and engrave things at nanoscale for materials, electrical, biochemical, physical, and life sciences. Further advancements in AFM technology, especially the non-contact mode in a vacuum, has enabled the AFM to achieve the dream of single-atom resolution, including the same silicon 7x7 reconstruction pattern that originally made the STM famous. It has produced high-resolution images of molecules and those with the STM by utilizing a CO functionalized tip. As nanoscale measurements have become more and more important to scientific and technological advancement, the AFM is becoming the foundation of the nanotechnology industry and instrumental in nanofabrication, the manufacture of tiny structures. AFMs now use conducting cantilevers to measure electric potentials in samples, while others use current delivered from the tip to measure conductivity and transport at the nanoscale. The technology has been an integral part of the failure analysis testing for semiconductors. With the rise of nanomaterials such as carbon nanotubes, AFM technology became the preferred tool for imaging nanostructures and other polymers. This has proven crucial to developing stronger, more effective materials to build with, create electronics, and develop exciting new technologies. AFMs are able to accurately measure interactions at an atomic level and changes in the properties of a sample after atomic rearrangement. In biology and biochemistry, they're used to image the structure of biological molecules, cellular components, and other biomaterial. Today, some even use AFMs to detect cancer by measuring the hardness of certain cells compared to their neighbors. The AFM has many advantages over optical and electron microscopes. It provides three-dimensional topographic data and can measure various physical properties with unprecedented spatial resolution. It works on almost any kind of surface and can operate in air, in a vacuum, or in liquid. It achieves atomic resolution in a vacuum and near atomic resolution in air. Its only limitations are that it's still cumbersome to operate and it's relatively slow. In the future, I hope the AFM will become as easy to use as an optical microscope and gain throughput as high as that of an electron microscope. I am amazed at how talented and innovative people continue to find new methods and new applications. This technology has grown more powerful and useful than I imagined, and I'm proud and humble to have been part of this incredible journey.